All right. So we'll first and foremost complete the derivation that we started in the previous lecture. Of course, the goal that we set for ourselves was as follows. We had this term in terms of P and Q and G prime. Yes, and we said just like in case of the Euler-Lagrange equation and its derivation, we could essentially get rid of the dependency on G and say that irrespective of this term being dependent on G, you can still infer that the term that's getting multiplied with G has to be 0, and that's because there were some specific test cases of G for which it has to vanish. So here we are going to have to do the same thing, but it's a little more involved because now there's not just dependency on G but also on G prime. So we had some term in the following form. Right? This is the kind of term we had. I am not sure if I had missed a half with the P here, but you'll see that P essentially was half of L y prime, that's the 2 times you take the partial of the Lagrangian with respect to y prime. The half would appear because of course in the Taylor series you have alpha squared by 2, so the half would get absorbed. I think I didn't explicitly write P and Q in the previous lecture, but instead chose to underline the parts, so you have to also embed the half within. Right? The point is that if this fellow is positive, then so is L y prime, because if there's a dependency of a half, that's just a scaling factor. Right? Now the question is, from this, if we want this to be greater than 0, what can we possibly say about P and Q individually, or bigger question, can we at all say anything about P and Q individually, because this term seems to depend both on G and G prime. And our hunch is that this G prime term perhaps predominates the G term. The reason being, the intuitive reason for this being the fact that after all, if this is A and this is B, this G, no matter what it does, it has to start at 0 and truncate at 0 again at the points A and B. So even if this G rises to a high value, which is essentially say the value of G, then what does G prime have to do? The higher you soar, the lower you'll have to dip, because eventually you'll have to end up here. And the extent, the rate at which it is going up is dependent on G prime. So if you were to choose a curve such as this, right, smooth curve, although it looks like sort of a gate function, but it's a smooth, it's not really an absolute square pulse. Now what do you think is going to be the value of this G prime for the majority of this interval? It's 0, right, because it's almost held to a constant value, or if it's slightly bent, then it's a negligible value. On the other hand, if this rise is quite steep and so is the fall, then what do you think is going to happen to the derivative in this small little interval? It's going to have a pretty high positive value in this interval and a pretty high negative value within this small little interval, and you can make this interval smaller and smaller so that the G prime, the derivative of G with respect to x, becomes really high. So while living within the class of perturbations which vanish at A and B, you can cook up such examples where even though the value of G is bounded, G prime can be made very high. In fact, you can make this interval smaller and smaller and G prime gets higher and higher. So this is the intuition that suggests to us that perhaps in this expression it is G prime that matters a lot more than G, and therefore the factor that multiplies G prime probably ought to govern the sign of this entire integrand. Yeah, that's the intuition. But of course we did slightly better than that. We actually gave an explicit expression for one such g. Remember what the g was? So we said that suppose p at x naught is negative. In fact, we said that suppose p at x naught is equal to minus twice beta, with beta being a positive real number. Suppose this is the case. And because of the continuity of p, what can we say? That it will certainly not jump from this negative value to a positive value instantaneously. So for a small little interval around x naught, so of course x naught belongs to the interval a to b. So you can always find a small little interval x naught minus epsilon to x naught plus epsilon, yeah, such that p x is smaller than, what is the value we had chosen? Minus beta. Okay, you can make it less than or equal to minus beta, does not matter, right. So it does not, it might rise from its negative value of minus 2 beta, but it does not rise beyond minus beta, because minus beta is higher on the y axis than minus 2 beta, right. Okay, now suppose this is the situation. So somehow p has managed to have a negative value at some point in this interval. Does this somehow rule out the possibility of us meeting this condition? That is the question. If it does, then we will be able to say that it is impossible to have p attain a negative value at any point in this interval between a and b. Can we establish that? So we took the following g. Once you have established that this is your chosen epsilon, let us define g in the following manner. For x belonging to x0 minus epsilon to x naught plus epsilon and 0 elsewhere in AB, which is essentially the semi-open or semi-closed interval between a and x0 minus epsilon union x0 plus epsilon to b. That is elsewhere, right, or the way we wrote, like deletion of this interval from this entire interval. So in the complementary part of that interval, this is what it attains. Now what happens to g prime x? Okay, I am sorry, I think we had chosen positive, right, the square of this thing, right, yeah, because of course you want this to stick to a positive value. Yeah. So what is this going to be? What is the derivative of this? So of course something has to be pulled out of here. Pi by epsilon has to be pulled out of here, right, and what happens to this? Just multiple of the angle, so sine of 2 pi upon epsilon x minus x naught for x in x naught minus epsilon to x naught plus epsilon, yes, and outside of course it's 0. Okay, that is kind of this function. Okay, fair enough. Now outside of this interval, this function vanishes. So I put it to you that if this integral is now evaluated, you need to only evaluate this integral over the interval x naught minus epsilon to x naught plus epsilon, because outside of it both g and g prime vanish, so it does not exist. So now let us look at this integral a to b px g prime squared plus qx gx squared dx, that's nothing but x naught minus epsilon to x naught plus epsilon px g prime x squared plus qx gx squared dx. Right? Now, quickly, if you want to bound this, what can we say? What is the range of values that px can attain within this? At most minus beta, because that's what we've said, that's how we've chose the epsilon to begin with. Yeah, so the maximum value that it can attain in this interval is minus beta. It will be worse than minus beta perhaps, going all the way up to minus 2 beta in fact, but the best it can do in terms of raising the value is minus beta. So this is less than or equal to minus beta integration x naught minus epsilon to x naught plus epsilon, and g prime x is this. So this is squared, so you have pi squared by epsilon squared, sine squared of this, right? What about this? The other term? Well, within this small little interval, q is bounded by, in its magnitude, by some number, say d. So suppose max of x belonging to x naught minus epsilon to x naught plus epsilon is d. Yeah. So of course this is then so g squared is, well, is that right? Is that clear? The first term, we're pulling out the p here. Second term, the d comes and substitutes this q, because the absolute value of q over the interval is, the maximum of that is defined to be d. Yes. So of course anything you do instead of d here is going to do worse, because this fellow is after all a quadratic thing. Yeah. So this is indeed the upper bound, right? I'll do one more thing here. Now this is of course bounded by 1. So instead of, like, you know, using all those tricks you learned for integration, fourth power, get it down to its quadratic and this, that, blah, 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 let's just say this is upper bounded by d x plus epsilon minus x minus epsilon, that's 2 epsilon. So 2d epsilon. That just takes care of this term, right? I'm being rather coarse in my approximation here. Okay, is this clear? This term is further upper bounded by this. What about this term now? Here we can actually do a little better, because okay, it's just sine squared, so why not beta by 2 and 2 sine squared. So quickly tell me, what's 2 sine squared theta? What does it remind you of? 1 minus 2 sine squared theta is equal to cos 2 theta, so 1 minus cos 2 theta. So this is minus beta by 2 integration from x naught minus epsilon to x naught plus epsilon. I can actually pull out the pi squared as well and the epsilon squared below. So this is 1 minus cos of 4 pi by epsilon x minus x naught. I hope that's correct. Dx. I've still maintained equality here, yeah. This is not really upper bounding this. I've just kind of used the trigonometric multiple and submultiple angle formula, so to say. Yes. What about the integral of this over the interval? Can you say something about it? You can actually directly integrate. It's cos theta, so its integral will be sin theta. Evaluated at both these points, what happens to sin theta? Well, it's a multiple, right? The epsilon will come in here. When you substitute x as x plus epsilon, it's just epsilon. When you substitute x as x minus epsilon, x naught minus epsilon, it comes as minus epsilon. So it's 4 pi and 4 pi. In either case, it's 0. So this part of the integral is 0. So the only part of the integral that survives is this. And what is that? It's 2 epsilon. Yes. So 2 epsilon and 2 epsilon squared get cancelled out, by dint of which we might write this as 2d epsilon minus pi squared beta upon epsilon, I hope, right? Yes. What is so special about this term now? What have we achieved after all? This is just some term that depends on this epsilon. So what's the big deal? What were we trying to do, remember? We were trying to infer something about p. So we said let p attain a negative value at some point in the interval. And then we constructed a perturbation like so and said, okay, if p attains a negative value, let me construct a perturbation like so which vanishes at a and b and has g and g prime given like so. In that case, let us test out what happens to this fellow. And now we see that if you make epsilon small, what would happen? D is positive, so the positive term is not dominating here, right? If you make epsilon smaller and smaller, you can get this pi squared beta by epsilon to shoot up really high, which means that the negative component in that term, that means this entire thing is less than or equal to some negative number if you let epsilon be really small. Of course, you will say, oh, okay, you chose the epsilon such as this, okay, fine, make the epsilon smaller. This one will still hold. If you have px sticking between minus beta and minus 2 beta within a small interval, if you make the interval even smaller, of course it will still stick around between minus 2 beta and minus beta. So you can always play around with the epsilon once you have made this initial choice of epsilon. You can still make epsilon smaller and smaller and none of these conditions are violated in the process. So all the arguments we have made here still carry forward, and in the process you've now achieved something. You've shown that this thing depends inversely on the epsilon, the negative component of it. So by making epsilon small, you'll actually be able to ensure that this term is actually negative. Which means what exactly? If you want to meet the condition that this is true, which comes from the second variation, you cannot allow px to attain negative value at any point in the interval. Because if you do, I'll construct a perturbation like this and establish that this term actually is negative, right? So based on all of this development here, we can just say that hence px should be greater than or equal to. Okay, we might go with greater than or equal to because we are only talking about necessary conditions right now. Yeah. So Necessary for what? For the extremal candidate that you have obtained from the solution of the Euler-Lagrange equation to actually possibly be a, right. Also, if you recall now the other statement we had made about this, now this P, recall what the P was? Px was actually half L y prime y prime. Yes? So what happens? P being, of course I am omitting the arguments of x, y and y prime here. Yeah, that is understood. So P being positive implies L y prime being positive. L y prime being positive implies the second derivative of the Hamiltonian with respect to z evaluated at y prime, which is the slope of the extremal at x, that was negative of minus L y prime, remember? We derived it the other day. So that then has to be negative, which means that subject to a choice of z equal to y prime, the Hamiltonian gets maximized. Of course, you need the strict inequality there, okay? But at least that's a hint towards the Hamiltonian being maximized if the third argument was replaced by y prime in the Hamiltonian, okay? That's just another hint towards the maximum principle. But we have some more work here pending. We are not done yet. All we have seen is that, okay, if you want this fellow or this fellow to meet this condition, then you better have Px non-negative in the entire interval, okay. So let's see how far we can infer from just this to begin with. An interesting question, can we do something similar about Q? Well, get back to the intuition that we presented right at the beginning. You see, think of that function. In fact, if you draw this sine squared pi by epsilon x minus x naught, you will immediately see that function also has the same nature, okay. It is bounded between 0 and 1, but the slope depends on epsilon. So if you choose epsilon to be really small, the slope goes unbounded. That is exactly the defect with this. That's why exactly the derivative term predominates, right? Which is why you can try as you might, but getting rid of the P dependent term and just inferring something about Q is not going to help, okay. Would have been ideally nice if we could say something about both P and Q, but as of now we can only infer that P is the only term that's required to be non-negative in the entire interval, okay.